Hi everyone, my name is Milad and today we'll be doing a system design practice exercise. I am doing these to help improve my skill set, but I hope in that process you guys learn something as well. Always double check anything you see or hear in my videos. There are people far more talented in system design than I am out there. If you do enjoy the video, please consider liking this video, leaving a comment, and if possible, subscribing. With that said, let's dive right into it. Alright, today I'll be designing an e-commerce website, and I will try to adhere to the following requirements. User authentication and authorization, implement secure login and user management, product catalog management, system for handling product listings, descriptions, and prices, shopping cart and order processing, enable customers to manage cart and process orders efficiently, payment processing, integrate with payment gateways for various payment methods, scalable and responsive architecture designed for high traffic handling and cross-device compatibility, and security and data protection, robust measures to secure transactions and user data. All right, well, we sure got a number of requirements here. So one of the things I can tell right away is we'll definitely be using a SQL database here. We'll have many relationships, orders, payments, carts, and maybe reviews. That's not included, but you have to try to scope out these ideas at the beginning. Additionally, we have to be asset compliant, especially for payment processing, PCI compliant. So one of the things we definitely have to do is make sure we create a pipeline specifically for security protocols when it involves sensitive information like credit card, bank information, and such. And when we talk about scalable and responsive architecture, that typically means an elastic infrastructure. So we'd be probably utilizing Kubernetes to allow us to auto scale our clusters, and within each cluster, each node, Kubernetes node, which can itself scale the individual pods that operate the services that we need. And let's see what else. Payment processing, shopping cart. Now, because we also want the ability to utilize cross-device, we want cross-device compatibility. That means instead of saving the information in, let's say, a browser cookie or session, we will associate that with a user, and that would require the user to log in. So this would be a two-step approach. One, if they're not logged in, save it on the browser, and if they are, save it to our system. All right, with that said, let's dive right into what I always like to start off with is the schema. The schema gives me an idea of the entities I'll be working with, and through that, I can understand the type of functionality I need, and more importantly, what those relationships look like. So, we start off with a user table, and because we're using a SQL database, we'll be using tables and columns as opposed to, let's say, we were using a non-SQL database. In which case we'd be using collections and documents. All right, and we have structured data here. So we have user ID, username, email, password, maybe phone number, not necessarily. We have a status ID, which is always good when you have an entity. This will allow us to put the user in different states. And let's see what else we need here. And I think that's pretty a good start. Once again, I'm doing the bare minimum. We're looking for a POC, and then we can expand past that. So always take this approach if you're trying to build something. Don't overextend. Don't let scope creep come in. And maybe a date stamp here as to when they joined. All right, so next thing I can think of is user order. and we have a user order ID. We have user ID, and then we have, let's say, cost total. Here we might want taxes, total taxes, because you could have many types of taxes, and we can have state tax ID, and maybe country. Country ID. Let's do country. And this is where this order was sent to. State. All right. And let's, for the sake of consistency, country, state ID. We definitely want a date stamp. We want a status ID. And let's see what other things we want to associate here. We've placed an order. The nature of order is there anything else we need here? Not that I can think of right now. We might need, okay, let's also do user address ID. And this allows us to know what address it went to. We can save the address string into the database. There might be an argument for that because a user can go later on and change that address. But when you delete information like that, you typically do not want to do a hard delete. You want to do a soft delete. And the soft delete basically means instead of deleting that data from your database, what you're doing is setting a flag that makes it invisible to all the users on the front end, but for auditing reason, you can still get that data. So let's go over here and do user address. And we got user ID, user address ID, and then obviously address, city, state, zip. Metadata, and we can have a status ID here. We can have a default flag is here, flag as well. So the status ID, once again, if the user deletes it, we can set the status to, let's say, -1, which means it's deleted. And later on, when we need to, let's say, a shipment goes out and it gets messed up, blah, 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 we can come back and look at where it went in case the user changed it in the process of that order being fulfilled. Next, we want user payment. And we have user payment ID. We have user ID. We have payment info, right? And this can be a variety of different info, payment type, ID. That will let us know what kind of payment it is, date stamp, when it was added, and as always, a status ID. Is this payment ID, is this payment method still available, etc. like that. So here, this can be a JSON value, or, you know, if you want to be a little bit more granular, we can update this to be user payment credit card, user payment bank, etc., etc. So for the sake of simplicity and for the sake of just getting to the architecture, we're going to keep an infrastructure. We're going to keep it to this. Next, we want, so we've placed an order. We want user order product that will let us know what products are associated to this order. There's two ways you can approach this when designating a primary ID. I'll simply do user ID and product ID. And these two combined will create the primary key. And then we want quantity. We want price per product, let's just say. that will let us know what the cost of this is. And then let's see, SKU. A big part of the order management is having the SKU, which is a universal value that's utilized across all businesses that deal with products. And then let's see what else we can put in here. That's all I can think of right now. We can come back and visit this later. We want a user order payment transaction. Let's call it transaction. This is an attempt to process the pay for the order, and we will do user order transaction ID. We will have user order ID. We will have user payment ID. We will have a status ID. We will have an amount here, date stamp, and we might even want a vendor ID here in case we have multiple vendors that can process payments for us. And the reason we have a one-to-many relationship here is because you can try to pay for an order and a card will get declined, and then you try a different one, or you pay partially for the order with one payment method and then the rest of it with one or more other payment methods. Next, we need product ID, and we need product ID, name, and other details. Let's say vendor ID, actually merchant ID, and status ID. Those let us know it's out of stock, discontinued, etc., etc. So let's do merchant ID, merchant ID, name. This is the merchant who's selling this product. And then other metadata information. As always, this is open-ended, status ID. And then we come here and we do merchant product, because there is an association to that user, to that product, to that. There's an association there. So then we got merchant product ID. We got the merchant ID, name, and then color, for example, and many other things. And let's just do meta, open-ended again, whatever business deems appropriate for this thing. All right, so we got that. And as always, whenever I use an ID within my schema, I want there to be an association to it. So we got a status table, and then we have name, description, maybe code, and so on, maybe a status ID. And if you want to extend this, you can categorize them, type ID, and actually you can do entity here. This means this ID, geez, wait a minute, that's funny, I had status ID instead of status ID. This means you can target statuses for specific entities. So you'll have a specific set of statuses for user address, and so on. And then since we're using entity, we need entity ID, we need an entity table. Entity ID, name, description, and that will do it. And maybe a status ID here, or whatever. You don't really need this, but it's just there. All right, so that gets us started with our database schema. I think this is good for now. Now let's type into this, this API process. All right, so let's start off with the easiest ones. We have API sign up. One thing you might want to do if you want to have version control is maybe include the version in the API. This way you can have legacy support, backwards compatibility and so forth, so that let's say somebody doesn't update their app and it points to the backend, what version API you need to support. All right, so for parameters, this is, let's say user name, email, and password. Then we have another post. We've got API v1 sign up, login. We have login here. And wait, let me get over here. Over here we get response will be JWT, which is a JSON web token. We will basically create a signed value that's stored in a JSON and pass it to the client, and the client will send that to us with every request, and we'll use that value to verify authenticate the user. And you can save other things besides the user information, like access information and whatever else you deemed appropriate. Okay, so over here we're logging in, and we'll send, let's just say they log in with their email for password. And once again, I'm keeping this to the bare minimum, just so that we can get to the rest of the system design. All right, so we've logged in. We want to do a post. Next, we want to do a post API v1 add. Let's do cart add, and we will send product ID, quantity, and that's basically all. And some, maybe you want some other information, but that's the very bare minimum. And you can always add additional information there as you want. Response will be, let's say, successful or an error. Next, we want to do, let's do post API v1, and we want to do checkout. We won't send anything there. We won't have any parameters there, but in the header, we will send back the access token, which is once again the JWT here. And we will get back we will get cart info. And in that cart info, we will have prices, sums, taxes, and everything else. Additionally, let's stop there and just move on to the next one. API v1 checkout payment. Here, let's just say we will do payment type ID. We will have payment info, and this will be the payment information, credit card information, banking information. If you're using mobile app, potentially Google Pay or Google Pay token or Apple token. And we will send that as well. So over here, We might also select address, ship to, address info, ship to user address ID. So that will contain where we're shipping it. The response, and obviously in the header, we will have the JWT. Once again, that's the access token. And the response will be order data, like order ID, etc., or an error. Could be payment failure, order ran out of stock, or something like that. Okay, next we want post. We want, let's see here, we will have, API v1. We will have user address add. We will have address data, address the state, country, etc. Header, JWT, or just access token. And the response will be confirmation or an error. Next, we will have pretty much the same thing here. Payment add. We will have payment type ID, payment info, and other information. For example, for credit cards, we might need addresses and etc. like that, confirmation, etc. So we've done that. We've added that. We want to get card. Let's see, do we have, okay, so now we want to, let me do this right here. Get API v1 user, let's just say cart. We will do, we don't need a parameter, but in the header we will send the access token, and we will get back cart info or error. Next we want, let's say get API v1 orders, or order, let's do order, and nothing in the, well, actually we will have filters here, optional filters. And whenever, as always, whenever you're getting an order, whenever you're working with a list, you'll always have an offset. This is for pagination purposes. And then in the header, we will have our access token, and then response will be order list or error. Next, we will have order ID, and that's pretty much it. You could actually, yep, access token and then order details info or error. All right. Let's see. That is, so this is getting pretty long, and I'm just gonna skip the product catalog management because that introduces a whole lot of other things, and we're already getting pretty detailed at this level. So this is much bigger system design than typically. So let's see how this thing works out, and then maybe we can revisit it and dive into the rest of it. So we're doing an e-commerce. We don't know where our customers are coming from. Perfect time to utilize a global load balancer. What is a global load balancer? Well, when you hit a URL, what happens is that it's directed to one or more servers. And these servers will either process your request or direct it down a path where it can get processed. And when you want to have high reliability, you want your system distributed. You want multiple data centers. And data centers are basically where your servers are hosted and you provide the service you want. So global load balancers, what they will do is direct your request to the most appropriate region to process your request. And when we're talking about a really high volume e-commerce website, we want multiple layers of load balancers because we want to have data centers in different countries, different states, depending on the volume, so that there is less overhead for the servers and data centers, and that we provide the most high efficient, fastest service. So once we get past the global load balancer, we're going to pass it to the regional load balancers. And the way the global load balancer will determine what regional load balancer to send you to is, on some very basic level, is what's up, what has the least latency, and what region is closest to you. Once you get to the regional load balancer, it's a little bit more complicated than that, but not so much. So the regional load balancers now, they determine what data center to send you to. And when we take a look at this, what that means is that these data centers, once again, where the servers are waiting to process your information, need to be directed your request. And the way it does that is either round robin or lowest load, or least latency, or weighted round robin, depending on what algorithm works best for you. If you have data centers that aren't all equal, some of them have more powerful servers. Let's say it's a more recent data center with more recent hardware, you might want to weigh the round robin, meaning more requests will go to that data center and are processed. And because we want to have an elastic infrastructure, that means we want our data centers to be able to manage and adapt to volume. Each data center will have in itself a local load balancer. Now, a local load balancer will determine what server within each data center is most appropriate to handle your request. And then when it finally determines what server should handle your request, we will finally hit our entry point into that service, which is called an API gateway. All right, so here we go. And we went from the global load balancer to the regional load balancer. We went from the regional load balancer to the local load balancer, and we went from the local load balancer to, that's right, the gateway. Now that we've hit our gateway, we have to determine what request we're going to handle first. So let's do user sign up and user login. So we will have our SQL database here, and because we want high volume here, we can definitely, depending on how popular the website is, let's say we're building Amazon, we definitely need massive amounts of processing capacity and scalability. MySQL is good, but what's best is NewSQL, which was designed with volume and with volume and scalability in mind, matching the scalability and flexibility of NoSQL databases. Here we will have user info. So a user comes in, they sign up, that information is passed on to a user service. And the user service is responsible for processing requests that pertain to the user entity. And the user service will then save that information into the database, and as well as check the cache. The cache is a type of storage that allows you to save information in memory as opposed to a hard disk. And the reason that's important is because memory access is significantly faster than hard drive access or SSD access, because it's very close. It's actually it's a far more efficient storage that's on the motherboard or has a much faster access time than what you would get from trying to access data on a hard drive, for example. And one of the most popular caching servers are Redis, and Redis has built-in scalability. So what you do is out of the box configure to scale and build clusters, and clusters are many Redis servers that connect together to create redundancy and partitioning. And partitioning is that when you have really high volume of data, it's impossible to save all that information in a single server. So what you do is you distribute it in a fashion where you will always know where that data lives on your servers. And one way of doing that is consistent hashing. Consistent hashing is an approach and an algorithm that allows you to hash a specific key for whatever data you're working with and always know what server is associated to it. So what happens when we sign up is the user service will check the cache. Hey, does this user exist? If not, it will then double check in the database to make sure that it's not simply the data didn't live in cache, to make sure whatever username or email that you're signing up with doesn't exist, and if so, send back a response that you have to try something different. Other than that, if it's successful, it saves it to the cache and to the database. Now, after that, what we can do is, now with the login, what happens is after they successfully log in, what we want to do next is provide our access token or our JWT, signed JSON Web Token, and we have an authorization service. So after a successful user sign up, the user service will hit the authentication service and send back that information. When a user logs in, the API gateway will first, when the user logs in, once again, we hit the user service, we verify the information, check the Redis server, see if the user's data is validated. If the user doesn't exist there, hit the database, hit the authentication service, get a WT access token, and send that back to the client. Okay, so that takes care of that. Next, we want to do add to cart. All right. So now what happens is we send a request to add to cart. First thing we do is we check the access token. what we do is we verify the token and make sure it's signed by our server and it's authenticated. And once it's authenticated, we know who the user is. And then we'll pass that request on to, let's call it, card service. Oh, geez. All right. Sometimes I'm always inconsistent with my capitalization. All right. So we have a card service. What that does is we save that information into cache so that it is easily accessible. And in addition to that, we also save it in our database for auditing, historical reasons, and potentially recovery reasons. All right, so that adds that. Another thing we can do prior to that is we can hit our product service. And the reason we would hit that first before doing anything else is we want to make sure that the product that was provided is valid. It actually exists within our system. And if in the process of looking at the product and adding it, somebody else didn't buy the last one, we can verify that. So we'll hit that. The product service will, now over here, we'll update our cache. It contains cart info, and now it also contains product info. So we will hit our cache here. And remember, I have a single Redis server image block here, but we would have clusters of them, and we could have designated clusters for different purposes and focuses. And that will hit the cache. It will also hit the database in case it doesn't find that information. And here we have cart and product. All right, so we've taken care of that. So we've added to cart. Next, what we want to do is, let's see, access, add to cart, now checkout. So now what we do is, let's say we have a checkout service here. And the API, once again, first it's the authentication service. It verifies that the user is authenticated. It then passes on that request to checkout service. Now the checkout service will call the cart service. The cart service will validate all the products are still available, get all the product information, then send all that information back to the checkout service. The checkout service will do its thing, calculate tax, price, etc. In addition to that, let's just say we have actually, nope, I'm sorry, let me get rid of that. In addition to that, we will also get the user addresses, and over here user payment service. And it will also get what available payment services are available. So over here, and what you get back is not the actual data, but you get tokens that are associated to the payments, identifications and stuff like that. And we have, because this is so important, when we talk about security, we will have a designated database specifically for payment info. This will be under additional layers of security and very restricted access to ensure that we can reduce the probability of getting that data hacked. And to stick with that thing, we will also have a dedicated payment info Redis cluster tied down. So what we'll send back is, let's see here, checkout process, where are my cart info, and over here addresses, address info, and payment. So multiple things, payment options. Now we can design this where as they're checking out, they add in new payment, and that just, for the sake of simplicity, let's just say that's not an option. You got to go somewhere and add that information prior to checking out. All right, so we do a checkout, we get our payment options, we get the user addresses, we get the product information, and now we want to send payment. All right. So the user hits pay. It will then we will first, once again, authenticate the request. Then we will we will then pass this on to a dedicated pipeline for payment processing. All right. Here we have payment processing service. Okay. So we have payment processing service. What we've received is a token of that payment service. We will then check. We will check the cache. To verify that data exists, that payment option exists. If we don't see it in there, we check our database. And we'll find it. If not, we'll send an error message back. And then once we've verified it, based on the payment type, we will hit a variety of different third-party API access points. Oops. Jeez. All right. So next, we will hit one of these many services And you can imagine them as a Google Pay endpoint. Let's say this is a credit card vendor that processes credit card payments for us. This is Apple Pay. This is Google Pay, and so on. We then depending on the results of that, we will so there are many ways you can approach this. One way we can do this is have a messaging queue. Now, a messaging queue is when you have high volumes of messages that you want to save in a database. You definitely want to utilize a messaging queue. It's basically a place where you publish messages and then you have subscribers who are interested in those messages. And when they see a new message, they take an action on it. So, and a common messaging queue service here is Kafka. Now, Kafka payment result. Now, Kafka is a very highly respected, highly scalable service that's fault tolerance and allows you to process high volumes of information. Okay, wait, let me just reduce the width of this. Jeez. Move that over here. Delete that. Write this here. And then have let's just call it an audit service, not audits, let's say saver service. Saver service, just for the sake of simplicity, that reads from the Kafka topic and then stores that information into the database server. All right. So if it is successful, it will write to a second topic and what we want to make sure is that no other service has access to this high secure area. So information only goes out. The only information that comes in is an initial request to process that payment, but what happens is there is a black box as far as all the other services are concerned, and the only way of knowing what happens is outward communication. So here, we will then write that, if it's a success, we will write it into a topic as, let's say, successful order or successful payment. And once again, this is the Kafka topic. And what we will have are order services. That will subscribe to this. And they will get information that they will then that will have cart information as well. They will check the cart order the card service, they say, hey, this payment was successful, and it'll have information with the products and everything else. They'll check it against the card, say, hey, is this all that there was in the order? And if so, process that order. If not, wait for the payment to continue. So then, if it verifies, yes, this payment covers the entire order, it then saves that information into the database. And if necessary, but not really, saves that information into cache as well. This really is a business decision, because anytime you start utilizing these services, that means you need more capacity, more power, more processing power, and that all comes with cost and complexity. Finally, once the order is complete, we'll have order data here as well. Now there's an argument to be made to maybe use a NoSQL database like MongoDB to store all the order information. That just means you need additional expertise, that adds additional complexity and overheads and configuration. So there are benefits, but there's a trade-off as well, and you got to determine if the investment is worth the return. Finally, once the order is processed, we will write into another topic and this will be an order topic. And here, once again, Kafka over here. Let's say ready orders, or we'll say orders ready for shipment. And then we will have the shipment service. It will it will grab the address and order information. I'll just, well, you know what, we could save all the information in here in the topic so that the shipment service simply has to order it. But even if all the information is there, we definitely want to do an additional layer of confirmation. And once again, this is a business decision that needs to be made, that we will argue the pros and cons. And the reason you want to do this verification is if from the time it was passed into this topic to the time you processed it, the order might have been canceled. And then let's see, shopping catalog, product catalog management, we're not doing that. We did authentication, shopping cart and order processing, we did that. Payment processing, we did that. Scalability architecture, let's dive into that. So here, our different services will be built on top of K8. K8 is Kubernetes. And what that means is you can configure that service to track, let's say, different metrics, let's see, CPU usage, memory usage, and based on thresholds, create additional pods where those services live in to help delegate the request to process them. And then each node that handles these pods has a max capacity limit. And if those are hit, we want an additional layer of scalability, and that's called cluster auto scaling. That means each KA node is monitored, and if it seems like it's passing its threshold, we will fire up additional KA nodes to help delegate that information, delegate those processing requests. For a database, this is where we will have a cluster of databases. That means multiple databases all interconnected. We do that for redundancy, we do that for backup, and we do that for performance. And now that we have these clusters of databases, I'll go back to a point I mentioned previously, is we can't simply save all the data in one database. It's just not possible, especially for high volume. So what we do is we shard the data. And sharding basically means you take a specific key, you hash it, and you use an algorithm to determine how you assign this specific value to a specific server, a specific shard. And one way of doing that is something called consistent hashing, where you use a specific algorithm that will always guarantee you that you'll be able to find a server that data lives on. And then additionally, one of the benefits of consistent hashing is when it comes to removing and adding servers, that specific algorithm makes it seamless. That's a whole topic in itself. I would encourage you to look into that if you're unfamiliar with it. Next, what we do, whenever one important point here is when you're sharding, it's really important to keep related data in the same shards, like order data, address data. If you don't plan this accordingly, you will have data in different shards, and that makes querying really complicated and prone to errors. So be very mindful of that. Same thing for our Redis. We will have Redis clusters. We will partition them according to consistent hashing and deal with that way. And then load balancing, obviously we want multiple data centers all over the world. And what we do is we set up monitoring, and if we see one specific region having high volume, we plan on adding additional data centers and splitting that region into more regions, or adding more powerful servers. And that is all I have for today, guys. I hope you enjoyed it. Please take a moment to leave a comment. I'm really looking for somebody to ask a question or suggest a different system design. And if you did like this video, please consider liking it and subscribing. Thank you so much. Have a wonderful day. Goodbye for now.